There are three varieties of problems that we'll be solving on friction. Objects that are sliding or resting on level ground, wherever the applied force is parallel to the surface, meaning it's parallel to the horizontal plane. Another variety would be for objects that are on level ground, but the applied force is acting at some angle. And then lastly, objects that are on an inclined plane. First, let's look at the case for forces on an object that's moving on level ground. An example of this might be a crate that's being pulled by means of a rope at a constant speed. So let's imagine that we have the ground, and on that ground is a crate. All right, this crate is being pulled by means of a rope, and we know that it's moving at a constant speed. This is very important in diagramming the forces that are involved. We know that the crate has mass, therefore it has weight. And weight is a force that always points in the downward direction, towards the center of the earth. We'll label this FW, or force of weight. Also notice that I'm indicating the forces are acting on the center of gravity of the object wherever possible. Now, according to Newton's second law, if an object is not accelerating in a particular direction, then it means all the forces acting on the object must be balanced. So if there's a downward force of the crate on the ground, then there must be an equal and opposite force of the ground on the crate. We call this force the normal force in this instance. And since weight acts downward, the normal force will point upward. Normal means perpendicular, and this force is perpendicular to the ground. We'll label this force Fn, or normal force. And again, we know that they are equal and opposite because the crate is not accelerating down toward the center of the earth, and it's not accelerating upward into the sky. In the vertical plane, it's at rest. The object is being pulled along by means of a rope. Since it doesn't mention that it's being pulled at a particular angle, then we can assume that the rope is parallel to the surface. So it's being pulled along in my diagram to the right, although we could just as easily have drawn it as if the crate were moving to the left. I like to call this force the applied force and label it as FA for force applied, because the force that's moving the crate is actually being applied by means of a rope. Now, the important part I mentioned earlier, that it's traveling at a constant speed. This gives us additional information. It tells us that the frictional force must be balancing the applied force. We know that friction is a force that opposes the motion of an object. That means it will always point in the opposite direction that the object is moving. But since it's moving at a constant speed, we know it's not accelerating. So by Newton's second law, all the forces acting must be balanced. The applied force is moving to the right. My frictional force will point to the left, and that force vector is equal and opposite in magnitude to the applied force. That is a key factor in solving many of these problems. In this case, we know that Fn must equal Fw. And we also know that the frictional force balances or is equal to the applied force. Access the next video in the series to see what would happen if we had an object that was being pulled by a rope or pushed by a handle at some angle instead of just parallel to the surface. This concludes my first video.